Don't worry, it's not going to be 8 pages of notes. It's not going to happen. We're going to focus on the stuff that you absolutely positively need to know to be successful on our test and, more importantly, the Eastern final. So a couple things. Usually when we start off with this topic, we talk about, just as a quick review, of solving linear inequalities. So the reason we do this is because your domain of logarithms is going to be based on solving these inequalities. For example, having log of base, let's say base 10 of x, the domain is always going to be whatever the input is here, and it has to be greater than 0. So when we solve these, it's just kind of a review of, okay, do you guys remember how to solve inequalities? Of course you do, right? We add 8 to both sides. 7x is less than 8, divide by 7, x is less than 8 over 7. So that's just a kind of a refresher. We're not going to do these. I'm not going to give you guys anything like that. And if there's a negative, if there happens to be a negative x, just remember to change the sign. Okay, so now, what is a logarithm? One of the few things I remember from my high school math, and I like my math teachers, kind of why I became a math teacher. But one thing that my senior year, my math teacher said, and it kind of just always stuck with me, it didn't make a lot of sense until I started teaching, was he said, a logarithm is an exponent. I was like, well, what does he mean by that? Why would he say a logarithm is an exponent? And then once I started teaching and working with logarithms, like, oh, okay, I know what he really meant to say. So what is a logarithm? Well, a logarithmic function is a function to the base a, where a is greater than 1 and a can equal 0. It actually should be greater than 0, not greater than 1. Because you can have a fraction there. So a is greater than 0 and a can equal 0 is denoted by y equals log base a of x. So here's how we read this. Log base a of x. And here's where my high school math teacher's words kind of like resonated with me. So he said a logarithm is an exponent, and what he meant by that is the logarithmic function is equal to the exponent. So anytime that you have a logarithmic equation, what's on the other side of that equation is going to be the exponent when you rearrange it into exponential notation. So a couple things to point out from here. Base a, it's still base a, right? So if it's a base for a logarithm, it's the same as the base for the exponent. Now the y, what it's equal to, is your exponent over here. And that's why my high school math teacher said that. A logarithm is equal to the exponent. And your input is just going to be your results of what your exponential equation is equal to. So a couple things to point out here, and we'll get back to this translating in a second. The domain for logarithmic functions are from 0 to infinity. If you remember exponential functions, the domain was all real numbers, and the range was 0 to infinity. Well, that's the opposite here. Here, the range is all real numbers. So the domain and the range flip-flop for exponential and logarithmic functions. And the reason why that happened is because the log function is the inverse of the exponential function. All x and y values are switched. I'm going to ask you a question later on today of how do you find the inverse? And finding the inverse, this is the key. Switch those x and y values and you can find the inverse that way. Example 3, change exponential statements to logarithmic statements. So the first thing, this might be the most important thing, is going between logs and exponents. So I'm going to write this thing down one more time. So log base a of x is equal to y. Remember, a logarithm is equal to the exponent. So this whole thing, when I set it equal to y, it's telling you that y is going to be the exponent of base a. So to go from logarithmic notation to exponential notation, I'm going to rewrite this. Base is base. So a to the y power is equal to x, right? And vice versa. So take a look at these first few problems. 1.2 to the third power is equal to m. This is my exponent. This is my base. When I change it to logarithmic notation, automatically, first thing you do is say it's equal to 3. It's going to be equal to the exponent. I'm going to rewrite this as log base 1.2. And the only thing missing is what you're taking the log of, which is m. Okay, so let's take a look at b. Base is base. This is my base. It's going to be the base of my logarithm. B is my exponent. That means that 9 is going to be left as my input. So the first thing I do when I have a logarithmic equation, when I'm trying to get a logarithmic equation, is I set it equal to the exponent. The logarithm is equal to that exponent. Now, log base e of 9. Yeah, a good question. Do you have to write LOG to get the answer? Yeah. This is the whole section is on logarithmic functions. So yes, thank you for asking that. Oh shoot, what happened? Okay, so yeah, good question. You have to write log? Yeah, every time. Every time. Okay, so let me get back to this. All right, so now this brings us to our first of special logarithms. There's 2 special ones. This is the first of the 2. You will never, ever, ever see log base e. Instead, it's so common that we give it another name. Log base e is what we call natural log. And it's so special that it has its own symbol. And we write it as, with a cursive usually, cursive ln. Now, why we put the L in front of the N when we say in English natural log, it probably was, I think it was developed by like maybe a French mathematician or maybe a Spanish mathematician. Because like I think French, similar to Spanish, is you put the descriptor after the noun. So you can think of it as like log naturel, or I don't know how they say it in French. But so we don't write log log base e. Instead, we write natural log ln. So this problem then is better represented by ln of 9 is equal to b. That's going to be the correct way that we write log base e. So it's ln, not log base e, right? So that's something you'll see, and it'll take some getting used to. All right, I want you guys to try C on your own. Okay, so just take about 15 seconds. Let's see if you got this, and then I'm going to show the answer. Then I just want to get a thumbs up if you guys. All right, so let's see. How many of you guys got, remember, exponent, base, input. So it's going to be equal to the exponent. Base is base, 24. So give me a thumbs up. How many guys got log base A of 24 is equal to 4? Good, 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 good. Well, all right. Okay, good, very good. All right, so now we're going to go the other direction. We're going to go from logarithmic notation to exponential notation. And again, the big idea, the big understanding, and this is what I learned from my math teacher, was whatever it's equal to, that's going to be your exponent. This base, and that's the same base. And now when we put it into exponential notation, we're going to set it equal to the input. So a to the 5th power is equal to 4, right? That's still your base. and then this is your exponent here, and now your input is what you set it equal to. But in this case, it's going to be the result. So whatever I raise a to the fifth to, my result is going to be 4. All right, so now B brings us to our second of two special logarithms. Looking at B, you might say, Mr. Bassler, you messed up. There's no base there. And I do mess up once in a while, but I didn't mess up this time. There is a base. So whenever you just see log with no base, this is called common log. And the reason we call it common log is because it's actually used a lot in research. The Richter scale is based on log base 10. Decibels for hearing is based on log base 10. pH levels, like pH balance. There used to be commercials for deodorant, strong enough for a man, but pH balance for a woman. They also like talk about like same thing for like hair shampoo. So this is called common log, and what it really is log base 10. But you won't see the 10 there ever. You'll just see an log. And when you see that, you know that that's common log, which is log base 10. So now what B really looks like is log base 10 of D is equal to -8, or in exponential form, 10 to the -8th power is equal to D. Okay, so again, it's not a mistake. You're just not gonna, if you just see log, that means it's base 10. Okay, so those are two special ones. They're so special, in fact, that they are on your calculator. If you look at above of the on button, you have ln and you have log. And if you look above log, it says 10 to the x. And if you look above ln, it says e to the x. So those buttons are already there. All right, let's look at C again. There's our old log base e, right? But more commonly known as natural log, right? So again, this is, if you need help, that's what it looks like, but you're not going to see that anymore. You're only going to see this. So when you see the ln or the natural log, remember it's base e. So to change the exponential notation, it's going to be e to the -3rd is equal to b. All right, try D on your own. So take about 15 seconds and change it from logarithmic form to exponential form. Okay. How many of you guys got 3 to the C is equal to 5? Give me a thumbs up. Okay, well, we get more than that. All right. Okay. All right. So now, one of the things we're going to have to do is part of the reason why we're learning this is because it's sometimes hard to solve logarithmic equations, and it's easier to change them into exponential equations. So for example, looking at this one, log base 4 of y plus 3 is equal to x. With the knowledge of exponential equations, I could just rewrite this as 4 to the x is equal to y plus 3. And now y is equal to 4 to the x minus 3. So this is a lot easier to graph and a lot easier to solve. Okay, similarly for b, if I want to get y by itself, the natural log of y is equal to x minus 1. Well, again, with knowledge of exponential notation, I can rewrite this as e to the x minus 1 is equal to y, right? So we won't do these. So now, evaluating logs. There used to be a time, not too long ago, when I first started teaching, that the calculators didn't have the special log features. And so this was the only way to solve for logarithms. But now they do. So before I show you guys how Desmos can help you, we're going to do it the old-fashioned way. And this just gets you a better idea of logarithms. So again, I'm going to write this for the third time now. Log base A of x is equal to y, and a to the y is equal to x. Okay, so this is how you go back and forth between logarithmic notation and exponential notation. So our first step is rewrite the log expression as an equation equal to y. So set it equal to y, set it equal to y, set it equal to y, set it equal to y. The reason we do this is because we're trying to answer the question of what do I raise 2 to, or 2 to get 16? What do I raise 3 to get 1 over 27? What do I raise 1/4 to get 4,096? What do I raise e to get the cube root of e? And that's why we put the y there, because the y is going to be that exponent that you raise it to get that. The next step is to change the log equation into exponential notation. So 2 to the y is equal to 16. Okay, so I go from logarithmic notation to exponential notation. Now, once I have it in exponential notation, it's a lot easier to work with. So I'm going to rewrite it in rewrite the exponential function so they have the same base. And this is a continuation of what we did last class. So I'm going to rewrite 16 so that it's base 2. And that's just going to be 2 to the y is equal to 2 to the 4th power. And lastly, you guessed it, set the exponents equal to each other. So y is equal to 4. So what that does is it answers the question, what do I raise 2 to get 16? Well, you raise it to the 4th power. So this whole thing, log base 2 of 16 is equal to 4. That's what that means. Now I said that technology has come a long way. Well, check this out. We used to not be able to evaluate logs of different bases. So we had to use different tricks to figure that out, but now you guys can. So look at Desmos functions log base 2 of 16 is equal to 4. So I know some of you guys are like, oh, you know, I just can't figure this out. You know, first, you know, we tell our kids in our house when they have meltdowns, we're like, okay, respira profundo, take a deep breath, relax. You have Desmos, right? You have a graphic calculator. So you're not helpless. You guys can figure this stuff out. So I don't want to see any blanks. You guys can figure this out. Okay, take a deep breath and use your resources, right? But for everyone else, okay, who likes the challenge, who likes to kind of figure these puzzles out, okay, here's what you could do. Set it equal to y, rewrite it into exponential notation, change to the same base, and set the exponents equal to each other. So log base 3 of 1 over 27 is just -3. Okay, that's another way to represent -3. And if you want proof of that, if you don't believe me, log base 3 of 1 divided by 27. Okay, so you can use this technology to help you answer your questions if you're stuck, right? And I still want to see you work. Don't just give me a whole bunch of page full of answers, but at least at least you have a way to check your answers. Now, the C is a little tough because we're kind of not as used to negative exponents as we could be. So, but you can still do it. So 1/4 to the y power is equal to 4,096. So you may be comfortable with your powers of 4, but like, for example, I gotta use my calculator. So I know that 4 to the 3rd is 64. So now 4 to the 4th is 256. 4 to the 5th is 1,024. 4 to the 6th is 4,096. So now, first block I showed it one way. So for you guys, I'll show it another way. Maybe you don't like to have it as 1/4. So you could change this and make it 4 to the -1st power to the y is equal to 4 to the 6th power. So now 4 to the -y is equal to 4 to the 6th. -y is equal to 6. Y is equal to -6. So what this means is log 1/4 of 4,096 is equal to -6. That's what this means. This means -6. All right, so now for D, I had to zoom in on this because the copy is not very clear. But what that says is the cube root of E. Now you could leave it like that, but I highly recommend we change it to exponential notation. So the cube root of E is the same thing as E to the 1/3 power. And now when I solve for this, remember natural log is base E. So all this is saying is E to the Y is equal to E to the 1/3. Y is equal to 1/3. All right, so I'm changing between exponential notation and logarithmic notation. Right now, this next thing you might say like, well, I know how to use my calculator. Do you? Right? So you're going to see questions like this where you need to evaluate it using your calculator. And so we're going to get practice on that. And I'm going to kind of push Desmos on you guys because I think it's a little easier to operate. But if you guys are comfortable using your graphic calculator, go ahead and use this. That's totally fine. All right. So the natural log of 15/3. Okay, well, functions, natural log 15 divided by 3. So about 1.61. All right, this next one, when you see LOG, remember it's base 10, common log. And in fact, there's a button for that already. So to do this problem, again, it's this log. Whenever you see log, that's what it is. And that was, let's see, 23/14. Close parentheses, the whole thing divided by -0.01. Okay, and what's nice about Desmos is that it's going to look exactly how it does on the page, right? So now you know you're doing it right. So -21.56. All right, I want everyone to try C. I'm going to give you the answer ahead of time so you know what to look for. 1.11. Okay, play around with your calculator, play around with either Desmos or using your graphic calculators, and let's see if you can get 1.11. Okay, take about 30 seconds. It'll take you that long to type things in, right? So let's see if you guys can get that. Okay, how many people, give me a thumbs up, were able to get that either on their graphic calculator or on Desmos? Very good. That's it? Okay, you guys got to get used to technology. All right, so let's try this on Desmos. Okay, so I'm gonna put in parentheses because I want to make sure I get the right answer. So my entire numerator is going to go in parentheses. So 3 log 80 close those parentheses minus natural log of 5, close those parentheses, close the outer parentheses, divided by, and I don't need those parentheses because they already gave me the fraction bar. So log 5 plus natural log of 20. And there's the 1.11. Okay. All right, so we can quickly talk about domain. There's not too much graphing for logarithms, but, and especially now using Desmos, it's going to be a lot easier. But I want to emphasize this, that in order for you to find a domain of a logarithmic function, you're going to set the input to greater than 0. And we're kind of used to that because when you have the square root, we set that to greater than or equal to 0. When you have something in the denominator, you set it to not equal to 0. So for logarithmic functions, whatever the input is, so this would be considered your input. Okay, you set that to greater than 0. Now, the reason why it's not greater than or equal to 0 is because there's nothing that you could put into your, you could raise it by that's going to get you 0. So what I mean by that is, let's say you have 4 here. Let's go x and equal to y. So now if you look at this equation here, 4 to the y is equal to x, where x is my input. And there's nothing that I could raise, 4 to that's going to give me 0. There's not even a negative number. So think about the input. Think about what y is. If I put -1, I get 1/4. If I put 0, I get 1. If I put 1/4, well, then I get just a smaller number, but it's never going to be 0 and it's never going to be 1. And that's why we set it to greater than 0. So, you could say, well, how am I supposed to study that? Okay, if you want to study that, then just know that whatever the input is, you're going to set it to greater than 0. But I really want you guys to understand the reason why. The reason we do this is because there's nothing that you're going to put in here that's going to give you a value of 0 or a negative number. That's why we set it equal to greater than 0. So now we say x is greater than -3. That's my domain. Okay, over here, this is already to the third power, so x is just greater than 0. Now, we're not going to ask you these kind of questions, but that's why in the beginning of the lesson, we had you, that's why we originally had it, where you practice solving quadratic inequalities, because those are a little tougher. We're not going to ask you to do that in this class, especially in this climate we're in right now. We don't have enough time. But the input has to be greater than 0. All right, so now graphing. We're going to do a very little on graphing, especially because you have Desmos, but it's not going to be a huge part of the Eastern final, but it will be on our test. And here's the trick for graphing. You maybe aren't as familiar with logarithms, but you sure are familiar with exponents. So if you remember, if I have the function y equals a to the x, then these 3 points are always going to be on there. You're going to have -1 and 1 over a. You're going to have 0 and 1. And you're going to have 1 and a. You're always going to have those 3 points. But look at these points and compare them to these points. All we did was switch the x and y values. And that's going to be useful for us when we're graphing, because sometimes it's hard to find good values for logarithmic functions. Okay. I'm going to go back up a second. Whoa. Oh, there we go. Oh, here it is. Okay. All right. I'm gonna this is all recorded, so you guys can go back to this. Okay. All right. So now, so it's going to be a lot easier for us to graph the exponential, because again, the logarithm is, first of all, it's not natural to us, and second of all, it's hard to find those points, even using Desmos. You have to be kind of creative with that. Okay. The other thing to remember is the asymptote for this is y equals 0, and the asymptote for this is x equals 0. So again, you see that change of x and y values, right? So to understand graphing logarithms, we're first going to get a good sense of graphing exponents, which we did last class. So for y equals 2 to the x, I'm going to use just 3 points, -1 and 1/2, 0 and 1, and 1 and 2. And for fun, I'll go 2 and 4. All right, so now here's what this graph looks like. So -1 and 1/2, 0 and 1, 1 and 2, 2 and 4. And I have an asymptote at y equals 0. So my domain for all exponents is always all real numbers. My range, if there's no shifting, is 0 to infinity. My x-intercept is none. because I'm never going to touch the x-axis. My y-intercept is 0, 1, and my asymptote is y equals 0. Now let's check out its inverse. The inverse of y equals 2 to the x is log base 2 of x. And again, in the past, it's been hard to find the values using our calculator. Now you can, but it's a lot easier to find the inverse by just graphing the exponential. So look at these values. 1 over 2, negative 1. 1, 0. 2, 1, 4, 2. All I did was I interchanged the x and y values. Now here's what the graph looks like. 1/2, negative 1. 1, 0. 2, 1, 4, 2. And I want to show you guys this. Y equals x, remember, that's the line of symmetry for inverse functions. And if you look at these two functions, they're mirror images of each other along the line y equals x, right? I'm not trying to like say like, oh, I got mad graphic skills. I'm just saying, look at it, they are, right? So now when I find my domain and range, it's just going to be the opposite of these. My domain is 0 to infinity. My range is all reals. Look at it, it's pointing down to infinity, it's going up to positive infinity. And then my x-intercept, there is one, it's 1, 0. I have no y-intercept, and my asymptote is x equals 0. Okay, so again, it's kind of natural to struggle with graphing logarithms, but if you know the inverse, if you could graph the exponents, which all of us can, then you could just flip-flop it and graph the logarithm that way. So let's try this again. Y equals 3 to the x. Negative 1, 1/3. 0, 1. 1, 3, 2, 9. Well, it's a little bit bigger than 2 to the x, right? So all right, let's plot these points. So negative 1, 1/3, 0, 1, 1, 3, 2, 9. And it has an asymptote at y equals 0. So again, my domain for all exponentials is negative infinity to infinity. My range is 0 to infinity. My x-intercept is none. My y-intercept is 0, 1. And my asymptote is y equals 0. Almost identical to this, right? Except that it goes up a little higher. How do you find the points? These are exponential functions. You just, those are common knowledge, right? You just pick x and find y. So negative 1 goes in for x, y is 1/3. 0 goes in for x, y is 1. 1 goes in for x, y is 3. 2 goes in for x, y is 9. So the reason why we start off with exponents is because that's what we're more familiar with. Now, to find the logarithms, I just switch the x and y values. So 1/3, negative 1. 1, 0. 3, 1, and 9, 2. So 1/3, negative 1. 1, 0, 3, 1, and 9, 2. And again, here's my line of symmetry. And what more importantly is it's a lot easier to answer these questions because they're just inverses of each other. My domain is 0 to infinity. My range is negative infinity to infinity. My x-intercept is 1, 0. My y-intercept is none. And my asymptote is x equals 0. So like I said before, technology has allowed us to come a long way with this. So before you couldn't graph logarithms easily, but now you can. Y equals functions log base 3 of x. Okay, so it looks similar to mine, I guess. More importantly, though, you have a table of values. Now, you can look here, you can see 0 is undefined, -1 is undefined, -2 is undefined, because the range, the domain is from 0 to infinity, not including 0. That's why 0 is still undefined. But if I want to get more points, then I could put decimals in. So for example, 1/3, right? We know that's -1. For example, 1/9 is -2, right? That's really small. It's hard to graph, but it's there. And 9 is 2. So you can use decimals to help you graph if you're struggling with how do I find points and how do I graph this accurately, right? But or you could do it this way. All right, so now we're going to try a couple of these. These questions, they span 2 pages, so I'm going to be going back and forth. When I graded first block, there were some kids that skipped this. This is like the most important section. This is a section that most kids get wrong. So don't skip these notes. If you have to go to the bathroom, make sure you watch the video again. All right, so this is just listed twice because I think the formatting issue, right? So natural log of x plus 1. Find a domain. Well, to get the domain, it's just the input. X greater than 0, so my domain is 0 to infinity. Graph this function. Well, I can graph it because natural log is something that's easy to find in the calculator. So I'm going to go here, I'm going to graph both of these, f inverse and f, on the same plane. So these are decimal approximations. I can't tell you what this is off the top of my head, so I have to use decimals. So I'm going to use that. Y equals the natural log of x, close parentheses, plus 1. Okay, it's shifted up 1. That does not affect my domain or my range. It just affects the way the graph looks. And I'm going to get some more points here. So I know that if I go on the decimal route, I'll get more points. So let's say instead of 0, which I know doesn't work, let's go with 0.5. And instead of -1, which I know doesn't work, I'm going to go with 0.25. Oops. And let's go to 5 just for reference. Okay, so I'm going to use these 5 points to graph my line. Again, it's not going to be accurate or perfect, but it's going to be a good sense of what this graph looks like. Okay, and this is what I want you guys to do for your test, is you're going to use this table of values. So f of x equals natural log of x plus 1. And all I did to get this table of values is I used decimals to generate points. So 0.25 is -0.4. 0.5 is 0.31. 1 was 1. 2 is 1.69. And 5 is 2.61. Okay, so 0.25 is -0.4, 0.5 is 0.31, 1 is 1, 2 is 1.69, and 5, 2, 3, 4, 5 is 2.61. So it looks something like this. Again, it's not going to be perfect, but it'll give us an idea of what this looks like. Okay, and for you to get credit, I mean, anybody could just do this, right? I've seen that on some people's pages. I'm like, nah, don't give me that. Give me a table of values, right? That's the least you could do. So now let's finish answering this question. Find the range. I know now the range is always going to be all real numbers, and the asymptote, unless there's a shift left or right, is going to be x equals 0. But now here's the question that students struggle with from previous years. How do I find the inverse? Well, this is what you guys just took a test on. So who could tell me, and I tried to give you guys a hint at the beginning of the session here, either in the chat or shout it out, how do you find the inverse of a function? So if I already have it as y equals the natural log of x plus 1, how do I find the inverse of this function? Yes, great. Switch the x and y values. Perfect. Thank you so much for saying that. Okay, so This is how we're going to find our inverse. And then once I find the inverse, I'm going to use the calculator to help me graph it. So I'm going to switch the x and y values. So x equals the natural log of y plus 1. And I'm going to solve for y. Minus 1, minus 1. X minus 1 is equal to the natural log of y. Remember, natural log is base e. So I rewrite this as e to the x minus 1 is equal to y. And that's my inverse, e to the x minus 1. So now to answer these questions, my domain, remember, exponentials domain is always all reals. And my range, well, it's just going to be the opposite. It's going to be the domain of this one. Small line, 0 to infinity. And how do I graph it? I'm going to use Desmos. I can't do this in my head. Nobody can. E is an irrational number. So e to the x minus 1. Well, actually, I could cheat a little bit, right? I know that it's just the inverse of this. So I could just switch those x and y values and find the inverse and graph it that way. Negative 0.4 and 0.25. 0.31, 0.5. 1, 1. 1.69, 2, 2.61, 5. If you don't like those numbers, it's okay to use Desmos to get new numbers. But I was trying to show you guys that you can just switch the tables. So let me get a different color here. Negative 0.4 and 0.25, 0.31 and 5.5, 1 and 1, 1.69 and 2, and 2.61 and 5. And there we go. Okay, it's not perfect, but you can clearly see the symmetrical relationship between those two graphs. All right. Again, last year's crew and year before that, they struggled with finding the inverse. Okay, that's one of the biggest things on the test that I remember. So I'm not going to graph any more of these. For graphing, remember, you could just use Desmos. Don't you dare leave them blank. Use Desmos to figure it out. Domain, let's talk about this one. The domain is just going to be whatever the input is greater than 0. So x is greater than 3. Okay. The range for logarithms is all real numbers. The asymptote is going to be x equals 3, right? But more importantly, is how do you find the inverse? Okay, so again, this is where my students struggled last year. So how do I find the inverse of this? First, y equals negative log base 2 of x minus 3. Second, as its own Saturday helped me out here, you switch the x and y values. And third, solve for y. Remember, this is my exponent. So 2 to the x, or sorry, I had to do something first. Divide by negative 1. You got to get rid of that negative x. The log has to be isolated. So negative x is equal to log base 2 of y minus 3. Now I rewrite it. 2 to the negative x is equal to y minus 3. Add 3 to both sides. Y is equal to 2 to the negative x plus 3. That's the inverse. 2 to the negative x plus 3. And my domain is all reals. And my range, well, it's going to be the domain of this. Y is greater than 3, or 3 to infinity. And the reason we see that is because of this. It's shifted up 3. All right, and we're not going to graph it by hand. I just want to show you guys, it's kind of neat to see the inverses of each other. Okay, so I'll write this down so I don't have to keep going back and forth. So y is equal to 2 to the negative x plus 3, and y is equal to negative log base 2 of x minus 3. So first, let's do the log. So y equals functions log base 2 of x minus 3 okay? That's the first one. You see how it shifted over 3? You see how the y, the x, the x-intercept is x equals 3? And now the next one I'm going to do is its inverse. Y equals 2 to the negative x plus 3. Okay. So we see that symmetry there. Okay, they do meet here. They have a common point, which makes sense when x and y switch. How does a letter or number become an exponent? You have to change it to exponential notation. I'm not sure I understand that question. Just come in and I gotta understand that question a little bit more. All right, so that's switching x and y. We're not gonna do this because we don't need to. Okay, so now this is key. All right, so this leads into the next lesson, and there'll be a ton of these problems. Your homework tonight is 24 questions, but I went through them. They're all just switching between exponential and logarithmic, so it's pretty fast. All right. So like here, change the logarithmic equation into exponential form. Remember, so this will be the fourth time I'm writing this. Log base a of x is equal to y. A to the y is equal to x. So sometimes we want to switch to exponential form because, you know, it's hard to answer the question of what do I raise 3 to get 4x minus 7? That's a hard question to answer, but I can rewrite it as 3 squared is equal to 4x minus 7. And 3 squared we know is just 9 plus 7 plus 7, 16 is equal to 4x. Divide by 4, x is equal to 4. Okay, we would not be able to answer that question if we left it in logarithmic form. But by changing it to exponential form, it's a much easier question. Same here for b, x to the second power is equal to 64. And now we solve. Take the square root of both sides. Don't forget plus or minus. So x is equal to plus or minus 8. But one of these does not work. Which one does not work? Which one does not work? Right. I can't have a negative 8. Okay, so now my only answer is x is equal to 8 because this number has to be greater than 0. Okay, this one here, you guys are gonna learn a trick next class to make this problem much easier. But for right now, the only trick we know is rewriting it in exponential form. So base is e, remember, so this is e to the 11th equals e to the x, or x is equal to 11. Okay, remember it's equal to the exponent, so 3 to the x is equal to 81. And now, you know, we could guess and check, or some of you guys will want to change 81 to have the same base. You could do that too. So 3 to the x is equal to 3 to the 4th, x is equal to 4. Now, for e, this is going, you're going to go into logarithmic form because you can't solve this. This is why logarithms are so used because it helps us solve for when you have a variable as an exponent. We have no way of doing this unless we have logarithms. So check this out. E, okay, that's going to be your base. So now it's natural log of 7 equals 3x minus 1. Natural log of 7 is a number. I know it's hard to believe and you think like it's going to be something weird. It's a number, right? So we're going to treat it like a number. So I'm going to add 1 to both sides. Natural log of 7 plus 1 is equal to 3x. And divide both sides by 3. X is equal to the natural log of 7 plus 1 all over 3. That's the exact answer. you can put it in your calculator and get a decimal approximation. But without logarithms, we have no way of getting that answer. I'm going to set up these other ones and not solve them because we only got 3 minutes left, and I want to make sure we get to this. This is kind of a neat problem, especially some of you guys are studying chemistry. So log base 2 of x squared minus 2 is equal to 4. So this is just 2 to the 4th power equals x squared minus 2. I will finish this one. So here, when we solve, over here we couldn't have a negative because we can't have a negative right there as our base. But here, I can have a negative for 18 because that does work because the entire thing is squared. So that's different. So don't think just because you have a negative is wrong. You got to think about where is that negative going to be inputted at. So this does work. Over here, 3 squared is equal to x squared plus 5x plus 3. You can solve that for fun later. Here, 4 to the negative 8 is equal to 16 to the x. Right, and this looks like a little tricky, but remember, 16 is a power of 4. So 4 to the negative 8 is equal to 4 to the 2x. 2x is equal to negative 8. X is equal to negative 4. All right, got 2 minutes left for kind of a fun problem. pH. pH of a chemical solution is given by the formula pH is equal to negative log 10 base 10 of H plus. Remember, in math class, we don't use base 10, but your science teachers might. Where H plus is the concentration of hydrogen ions in moles per liter. The value of the pH ranges from 0, which is acidic, to 14, which is alkaline. What is the pH for these solutions? So they're basically telling us, put this in your calculator. And when you put that in your calculator, you get, and there's gonna be a little trick to this you guys will figure out. You get 4. This means that it has a pH of 4, all right, which is not acidic, but leaning towards acidic. Okay, over here, this is negative log of 0.000001, and that's a pH of 5. Right, and its shortcut is, if you count the number of zeros, 1, 2, 3, 4, 5, okay, this is really 10 to the negative 5th power. So you're taking the log base 10 of 10 to the negative 5th power. Over here, without a calculator, you could do this, 1, 2, 3, 4, 5, 6, this is 10 to the negative 6th power. So negative log of 10 to the negative 6 is just 6, right? This negative kind of, when you're going to multiply this negative with this negative 6 to make that positive 6. So what happens to the pH hydrogen ion as the concentration decreases? So as the concentration of hydrogen decreases, your pH increases. We see that here, as you get smaller pH, smaller hydrogen, you get higher pH. What is it when you have a pH of 3.8? So you're going to set this up. 3.8 is equal to negative log of H hydrogen plus. So my students who did this last year, who were in chemistry, they said, oh, well, for our teachers, all we do is say that it's 10 to the negative 3.8 power. And I was like, oh, so you guys know the shortcut, but the reason why is because of the algebra that we did here, right? So their teachers give them a little shortcut to figure this out. And so for 7.2, this would just be 7.2 to the negative 10 to the negative 7.2 power.